There are two types of two sample mean test. So first one is for, okay, so the first one is for unequal variance. Means, so basically this is for comparing two samples, right? So this is for comparing unequal, okay, for two independent samples. So we have two independent samples or groups, and we want to compare the sample means of that. Compare two independent sample means, whatever is the mean. But the variance of them is unequal. So each sample will have their own sample variance. So S1 and S2, they are not equal. That's there, and there are two chances, right? They can be equal also. So we'll see that next. So but when S1 is not equal to S2, the sample standard deviation, okay, this is S1 square. S1 is the standard deviation. This is your variance. Okay, it will be the same. Okay, so are significantly different from each other. That's what we have to do. So what will be the test statistic? Again, I'll just go this. You should just know the formula here, and then we'll do a problem. It will become very obvious. So my test statistic would be T is equal to difference of the two means, as I mentioned, and there will be some form of standard deviation in the bottom to normalize or standardize it, some scaling factor, and this will be equal to S1 square by N1 plus S2 square by N2. These are your sample means. These are sample standard deviation, and this is your sample size. Okay, and but the degrees of freedom, the way you calculate here is this is also called Welch formula. Welch. Okay, so the degrees of freedom here, it is because the variance is unequal, the degrees of freedom calculation is a bit different. So we calculate, so this is given like this. Okay, so it is kind of V, sorry. Okay, so this is given by, the formula is S1 square. So S1, it is a bit different. S1 square by N1 by S2 square by N2 whole square. Okay, and then divided by S1 to the power 4 by N1 square into N1 minus 1 and S2 to the power 4, it is symmetric, N2 square into N2 minus 1. So this is how we calculate the degrees of freedom. So this is coming from, so this was given by a mathematician called Welch and Satterwhite. Okay, so but we know it as Welch's formula. Okay, the second name is a bit difficult to pronounce. So this is the degrees of freedom, how we calculate it. Okay, so this is for unequal variance. So this is your mean difference by, this is your standard deviation of the first sample, standard deviation of the second sample, or the variance of first sample, variance of second sample, and scaled by the sample size. And then the degrees of freedom, we have a complex formula. This is generally computed separately. And the other second case would be that equal variance. Both the samples variance is equal, that is S1 square is equal to S2 square. In this case, okay, in this case, what do? That we create, we have a pooled variance now, because both are same. Now we create a pooled variance including their degrees of freedom, because the degrees of freedom is included for capturing the variance or variability in the data. How many independent data points are there which can be used for capturing the variance in the data. So this includes all those degrees of freedom also in this, and you will see the pooled variance formula. Earlier in the Cohen D, when we are discussing effect size, even there you would see a similar formula. Just go and check that. So I'll put the link of that video. So even in that video we have a similar pooled standard deviation. Okay, so pooled variance, here we have pooled variance. There we had variance and standard deviation are same. Standard deviation is just the square root of variance, so it is same. So this is given by S square of P, pooled. Okay, and this is N1 minus 1, okay, into S1 square plus N2 minus 1 into S2 square by sum of the degrees of freedom, N1 plus N2 minus 2. So this is like, if you read it, this is equal to N1 minus 1 plus N2 minus 2, N2 minus 1. So this is nothing but the sum of the two degrees of freedom for both the samples. Both have equal variance, so we can just add them up. Here also these are the degrees of freedom which are multiplied, and this is like kind of summation. So we have a pooled variance now, and this will be included in our test statistic. So what will be our test statistic? My test statistic in this would be, earlier we have written the test statistic, right? Yeah. Test statistic T is equal to similar x1 bar minus x2 bar, the sample means of the two independent different samples what we have, and then the pooled variance will come out and into 1 by n1 plus 1 by n2. Similar stuff, okay, if you see, because this pooled variance is common in both, it has come out, and 1 by n1 plus 1 by n2 remains constant. If you see in the same format, it can be written here also. x1 bar minus x2 bar by, if you put this sp inside the this one inside, it will become s square p by n1 plus s square p by n2. Okay, now you see both have taken the same form. If you see here, this was independent, and here we have the pooled variance including the degrees of freedom. Okay, and now here the degrees of freedom will become, here the degrees of freedom v will be equal to n1 plus n2 minus 2, that is equal to n1 minus 1 plus n2 minus 1. So that's what we have seen earlier in the one sample test also. So that's why it is coming like this. Okay, let's quickly solve a problem here and you will understand. So I have a question for you. So we have an AI team that wants to validate if the new ML model they have created, whether its accuracy is better than the existing or the old algorithm or old model, ML model. Okay, so we have an AI team and we have the data for each of them. Okay, AI team wants to validate, and they can perform a 2 sample t-test because there is a 2 independent model data. Wants to validate whether if the new ML model's accuracy is better than the accuracy of the existing or old algorithm. Kind of A/B testing. That's what they want to do. So they have some sample around that. So they will have some sample size, and then they will have sample mean, and they will have sample standard deviation for both of them. So let's say we have new, let's say, and then we have old. Let's say this is B. Okay. So NA is equal to 24 and B is equal to 18. Okay, and the X bar A, this is sample. Okay, this is 91%, and this XB bar is equal to 88%. This is your accuracy. The old model is 88%, the new one is 91%, and the standard deviation for A is 4%. Okay, not a 4%, 4, and this is 3 only. Okay, this is the data you have, and then assumption is, we assume that the population variance of both the samples is almost same. So we assume that nothing is given. So assumption is that population variance is of A is approximately equal to A. Both are approximately equal. So since the population variance is same, we can use the second equal variance test. Okay, or standard or population or the sample variance. Okay, both are same. Yeah, the first one was unequal variance. The second form was equal variance. I'll use this test now. So this will be my test statistic. So for this, I need to calculate the pooled standard deviation, and then we just put plug all the values in the formula and get the formula. This is just simple maths. So let's do it quickly. So before, this is hypothesis testing. So we have to go via the same route. So what is my null hypothesis? I use a different. Null hypothesis is that accuracy of new ML algorithm is equal to the old algorithm. Nothing has changed, status quo. So accuracy of new ML algo A is equal to accuracy whatever is equal to B's. Okay, B's accuracy. Simple. Nothing has changed. But HA says that, alternate hypothesis says that accuracy of A is greater than accuracy of B. Since this is greater, so again this will be a right tail test. So I'm just using the simple right tail test so that to give you the intuition of the, if it is less, then you will go to the left tail test. Okay, if it is not equal, then you will do two-sided. Okay, so let's compute the pooled standard deviation or variance. So pooled variance S square P. This is your pooled variance test. What is the formula for that? So this is your N1 minus 1 S1 square plus N2 minus 1, this one, N1 minus 1 S1 square, N2 minus 1 S1 square, N1 plus N2 minus 2. S1 square plus N2 minus 1 S2 square by N1 plus N2 minus 2. So let's do have computed it already. So N1 is 24, 24 minus 1 into S1 is standard deviation of the first one. So that is A, that is 4 square 16 plus N2 is 18 minus 1, second standard deviation is 3. So this is into 3 square by N1 plus N2 minus 2. So this is your 24 plus 18 minus 2. So this will be equal to 23 into 16 plus 17 into 9 by 24, 18, 42 by 40. So this will be, if you calculate it right, this will come out to be, just do a simple math, this will come out to be approximately 2.67. Okay, no, not 2.67, sorry, this will come out to be, that is the final value, this will be approximately 13. Okay, this will come out to be approximately 13. And then the test statistic says that this will be x1 bar minus x2 bar by pooled this into square root of 1 by n1 plus 1 by n2. Let's put the numbers. First mean is 91, 80, 88. So this is 91 minus 88 by, so this is S square P. So SP would be, SP is equal to square root of 13. This would be equal to, what will be square root of 13 equal to? This will be approximately equal to 3.6. Just check that again. So 3.6 into square root of 1 by n1. n1 is 24 and n1 is 24 and n2 is 18. A and B are 1 and 2. Okay, so 1 by 24 plus 1 by 18. 1 by 18. So if you calculate, this is 3 by 3.6 square root of 1 by 24 plus 1 by 18. If you compute this finally, this will come out to be approximately, this will be 2.67. Okay, do the math. This is simple. You can do it. The main thing is idea. Okay, I won't do the maths. So, and what is my degrees of freedom? Here in the pooled variance test, n1 plus n2 minus 2, this is 24 plus 18 minus 2, that is equal to 40. So let's compute the T alpha. So alpha, let it be again 0.05 or 5%. This will be equal to, what will be, so what all values I need? I need that, this is my 0.05 and I need my degrees of freedom. My degrees of freedom is equal to 40. So let's check the table again and find out what is the degrees of freedom in this table itself. So this is your same table, T.95, that is 0.05 is my one tail test. And then here you go just down in this column, here in this value, okay, and go to 40. So if see 40, and if I keep traveling in the 0.05, this is 0.05, this one column, and come to 40, 40, 40, 40. This will be 1.684. If you see the value, I'll highlight this. 1.684. Okay, so this will be equal to, see the table, okay, 1.684. So if you see again, quickly plot it initially I'll advise you to keep plotting it so that you get an idea. So this is symmetric, and your 0 is here. P alpha is equal to 1.684, and my T observed, this is your T observed, right? My T observed is clearly 2.67, okay, 1 unit ahead. So this was my rejection region, or this is my where alpha is equal to 5%, and this is your P value, which is definitely, this is for probability of observing T greater than or equal to T observed. So this value is definitely less than the critical value, or the area under the curve is less than 5%. So we reject null hypothesis finally and accept alternate hypothesis. And what does the alternate hypothesis say? That the new algo is significantly better than old algo. The accuracy, the new algo's accuracy, in terms of accuracy. Okay, that's what we are comparing. That's what was our alternate hypothesis. Accuracy of A is greater than B. So this is your, is significantly higher than this, because we have rejected the null hypothesis and the new model is performing better.